Hello and welcome to Lecture 13 of Math 2RO3. In today's lecture, we're going to be looking at section 3.D in the textbook, and we're going to continue our discussion on invertibility and isomorphisms. So this is actually the last section corresponding to chapter 3. And one of the big things we're going to see in today's lecture is kind of how we can think of linear maps as matrix multiplication. We're going to try to make this identification between the two. Okay, so just to kind of a recap of where we are, in the last lecture we saw that two finite dimensional vector spaces, V and W, are isomorphic if their dimensions are the same. And one thing that we've seen over the last two lectures is given a linear map from V to W, and if we put a basis V1 to Vn on the vector space V, and a basis W1 to Wm on my vector space W, then there's a matrix associated to this linear map, and it's the map where the kth column or the jth column is given by the coefficients after you write the jth basis element with respect to the basis elements of W. Okay, so remember this is the image of the jth basis element. So there's another way to think about what we're doing here is that we're actually giving a map from the set of all linear maps from V to W to the set of all M by N matrices. So remember what this is. This is all M by N matrices with entries inside of F. So you can think about what we're doing is we're taking linear map and we're mapping it over to a matrix MT. So part of the reason we sometimes use this notation is we can think of this notation here as representing the image of a particular map. Now on both sides I have vector spaces, and in fact there's a lot more structure going on here. What we have is if we think of what I've just written above here as a map identifying a linear map with a matrix, the function m or script m is actually an isomorphism. Okay, that is, this vector space is isomorphic to this vector space of all the m by n matrices. And the proof reduces to showing a bunch of things. And I won't write them all out, but I will write out some of the details. So first you have to show that M is a linear map. But this actually isn't so hard because this follows from what we've seen before, namely that if you take the sum of two linear maps, that's the same thing as taking M evaluated at T and M evaluated at S. So this matrix on the left side is the sum of the two matrices on the right side. And one of the other properties that we saw is that if you take the matrix associated to a scalar product of a linear map, that's the same thing as taking the scalar of the matrix that you get by taking the linear map S. So these two things here show us that we can view M as a linear map between these two vector spaces. And then what you need to do is, and I'll leave this for you, is now you need to check that M, thinking of M as a function, is injective and surjective. Okay, the details aren't too hard, but I'll leave them for you. Okay, so left for you to do. Okay, so what does that mean? What do we get out of this? Well, we can now think of LVW, the set of all linear maps, as being isomorphic to the set of all M by N matrices. So the first thing that we get out of this is that the dimension of this vector space is actually equal to the dimension of V times the dimension of W. Okay, and why is that? Well, it's because this space here is isomorphic to the space of M by N matrices, right? So we have the fact that the dimension of LVW has to be the same as the dimension of the set of m by n matrices because these two spaces are isomorphic. We know how big this space is, m times n, and that's the same thing as the dimension of V times the dimension of W. Okay, so to wrap up this first part of today's lecture is I just want to kind of get across the big idea. And the big idea that you should think about is that LVW, this vector space, is the same, and I'll put that in quotation marks, as the set of m by n matrices. So as we go on in the course, we're going to be spending a lot of time focusing on this vector space. But because of this theorem, what you may want to realize is, oh, what we're doing is we're actually studying the set of m by n matrices. But instead of thinking of our objects as matrices, we're thinking of our objects as being linear maps. So that's kind of the big idea you want to take away from this first part. So I'll stop right here, and I'll see you in part 2.